All glucose are equal, but some are more equal than others. If this physiological reference to the dystopian novel Animal Farm confuses you, imagine how David Kipnis and his colleagues must have felt when they discovered this reality in 1967. They call this strange phenomenon the incretin effect. But to understand its relevance to our discussion on anti-diabetics, we need to take our minds back on a journey to the genesis of endocrinology. So, welcome back to my YouTube channel. I advise you to tighten your seatbelts, as this is a 3-part series on the research that led to the discovery of the most profitable drug today. Early physicians believed that the neural networks seen as they examined cadavers solely controlled organ communication and function. However, this school of thought was debunked when William Bayliss and Ernest Sterling set out to determine the nerves responsible for the alkaline secretion of the pancreas into the intestine after a meal. The isolated sections of the digestive tract of dogs, severing all nervous connections to the pancreas. Simulating acidic chyme entering the small intestine, they injected the duodenum with hydrochloric acid. They observed that the pancreas still secreted bicarbonate to neutralize the chyme entering the intestine. Since all nervous influence had been cut off, they postulated that chemical messengers must have been released from the intestine into the bloodstream, which traveled to the pancreas, where the release of sodium bicarbonate into the intestine was initiated. These novel chemical messengers, synthesized in one organ and transported through the bloodstream to excite another organ, were termed hormones, and the hormones secreted by the pancreas to regulate intestinal pH they named secretin. As usual, enlightenment begets more curiosity, so scientists intensified research into this new field of endocrinology. Foremost among them was a Belgian physiologist, Jean Labère. He had read research work where secretin obtained from the duodenum could be purified with acidified 90% alcohol. While replicating this study, Jean observed that the fraction partitioned into the acidified alcohol acted like an amplified version of the crude secretin, stimulating an enormous secretion of bicarbonates from the pancreas. However, the residue left behind produced very little secretagogue activity, but surprisingly suppressed blood sugar levels. Understandably, scientists shifted from the nervous model to the hormonal model and assumed that all hypoglycemic activities observed within man must be due to insulin, which was the only hypoglycemic hormone at the time. So, when it was discovered that secretin also suppressed blood glucose levels, everyone just assumed that it must contain trace amounts of insulin. Jean, however, knew that since insulin was already a staple in diabetes therapy, his work would only be relevant if he could disprove these assumptions. He incubated large doses of the crude secretin in a pepsin hydrochloric acid mixture, which mimics stomach acid, in a bid to denature the insulin, and then heated the mixture to inactivate pepsin, before then partitioning it with 90% alcohol. He went ahead to inject this insulin-free residue into experimental dogs and was pleased to still observe a reduction in the blood glucose levels, establishing that the hypoglycemic secretin fraction possessed something other than insulin that regulates blood glucose levels. Jean decided to refer to this yet to be identified hypoglycemic hormone as incretin. Further research on hypoglycemic hormones other than insulin stalled until the discovery mentioned at the start of this video. When McIntyre and his team administered glucose both intravenously and directly to the intestine of individuals, they observed that the plasma insulin levels after intestinal administration were oddly higher, as though something within the intestine potentiated the excitation of the pancreas to insulin. Michael Perley and David Kipnis at the Washington University of Medicine attempted to standardize the data observed for McIntyre, so they administered 100 grams of oral glucose to normal weight, obese, normal weight diabetic, and obese diabetic subjects. To compare both routes, they administered an equivalent amount of intravenous glucose that would result in a similar arterial blood glucose curve after 3 hours of oral ingestion or in all test groups. They noticed that the plasma insulin response to intravenous glucose averaged between 30 to 40% lower than those seen after oral glucose ingestion. The maximal plasma insulin levels were also reached in about 30 minutes after oral administration, whereas it took about 60 minutes after intravenous infusion to attain similar plasma insulin levels, despite peak blood sugar levels from both routes occurring at the same time. This indicated that there was a delayed insulin response from intravenous administration. They also noticed that insulin secretion was influenced by body weight, as obese individuals secreted 3 to 5 times more insulin in both normal and diabetic subjects, irrespective of the route of administration. Obese diabetic subjects, however, secreted significantly less insulin when compared to their obese non-diabetic counterparts. It was then postulated that obesity increased insulin secretion because muscle and fat cells became intolerant of insulin stimulation and poorly utilized carbohydrates. They needed to test this out, and since the liver takes up approximately 2/3 of the oral glucose load after eating before it can even reach the peripheral circulation, they demonstrated the effect of poor glucose tolerance by measuring the liver's initial hepatic uptake after oral ingestion of glucose. In normal individuals, approximately 31 grams of a 100-gram oral glucose load enter the peripheral circulation. In normal weight diabetic subjects, on the other hand, over 50% of the oral glucose load entered the peripheral circulation, while as much as 75% of absorbed glucose load entered the bloodstream in obese diabetic patients. Note, this would mean that only 25% of that glucose load will be available to be absorbed by the liver in obese diabetic patients. Seeing this data, they postulated that this insulin intolerance was largely because the pancreatic beta cell secretory responsiveness to the incretin alimentary stimulus was depressed in diabetics. The pancreas couldn't react fast enough to the incretin signal of food in the intestine. This resulted in the subpar initial increase in the liver's insulin level within its portal vein and a delayed rise of peripheral plasma insulin level, which is characteristic of type 2 diabetes. Since hepatic glucose uptake is an insulin-dependent process, a large proportion of the ingested glucose will escape hepatic uptake in diabetes and enter the peripheral circulation, leading to the high level of glucose seen. This research work established new facts. An alimentary mechanism ensures a rapid and strong sensitization of the pancreas to release more insulin. So even before glucose was absorbed into the bloodstream, its presence in the intestine naturally stimulated insulin release first in the portal veins of the liver before doing the same in the general circulation. Type 2 diabetes also occurs when incretin from the intestine is not able to stimulate pancreatic secretion of insulin fast enough, such that most of the absorbed glucose is not being stored by the liver during the hepatic first pass, but finds its way into the bloodstream. The high amount of glucose escaping into the bloodstream explains the glucosuria noticed in diabetes and subsequent weight gain, since most of the absorbed sugar is not stored in the liver as expected, but rather within the adipose tissue and muscles as fat. It was also easy to understand why diabetics are always hungry, as the liver stores of energy are so underutilized that they can't provide enough glucose for the body's energy needs in the postprandial period, necessitating regular food intake. It was clear to everyone in diabetes research that they've been fighting the wrong culprit. Insulin was the chill guy who had been falsely accused for the inefficiency of the incretin hormones. But what really are these incretins? Could they be isolated and formulated into medications that augment the deteriorating incretin function in diabetics? Could they even have other functions aside from exciting the pancreas to secrete insulin? The next part in our Gods to Glory series will delve into the answers to these questions.